So what we'll do in the next 3 lectures, actually the 4th lecture right now, we'll move from the deep learning part to the acceleration part, but we'll try to type together. And again, we'll speak why we need special architecture for machine learning. And we'll discuss, this class will be very general description of mainly of CPU, GPU. It will give you the background also to programming CUDA, OpenCL. I think that will program CUDA and you'll start really program GPUs. You see that although CUDA written in C or C++, it's much different from programming regular programs. More than that, it is very important to understand the different architecture in order to program it correctly. And the next class will extend the discussion about many research in the area of learning on accelerators. And the class after that will focus on special hardware for the inference. And we'll see that today it is a little bit different because most of the learning is done on GPUs or something which is similar to GPU. But most of the inference today, at least this is the trend, is moving more and more to where FPGAs and ASICs or special purpose architectures. And again, we'll discuss why the differences and what are the differences. But again, the purpose of this session is, first of all, that you understand the differences, then that you will be able to program it. And I can tell you that research that we've done on CUDA or programming in this kind of languages showed that to write and run code on CUDA can take you a day. It's very, very simple. It's not very complicated. To optimize it, to get the maximum performance, can take you a few months. It depends on the size of the program. So, just to write something, it's not very, very difficult. But all the papers that you see, they have 10 times performance than CPUs, 100 times performance than CPUs. Usually it takes them a long time to optimize the system. Many of them are doing some tricks that they optimize the CPU, the GPU, and not the CPU, and then the gap is very, very high, but forget about it. The real numbers is usually you can get at least 10x on GPUs or similar on training than on CPUs. Usually we'll talk about it and we'll see that the CPUs try to close the gap later. Okay, so first of all, okay. So what we'll cover, so first of all we'll cover a little bit about why we care about computer architecture in general, and the answer is quite simple. And then we'll talk about the differences between CPU and GPUs, and then we move to GPU architecture, and in particular this time we'll focus on Nvidia, although I can tell you that in the last few months AMD are coming with new architecture for GPUs that gives a fair competition to Nvidia. We'll cover it maybe next week.
Who is AMD?
AMD.
AMD.
Yeah. Just a few historical notes. In the past, there were 2 big companies for GPUs. One, it was Nvidia, and the other was ATI. ATI was bought by AMD. And as in many cases, the purely architecture of AMD was much better than Nvidia. So why Nvidia won? Because Nvidia understood that the really trick in programming GPUs is the software hardware interfaces. So therefore, the day one, or the zero, they developed the system as co-designed between software and hardware, and we'll see it later on. While AMD, they gave 2 students in a summer job to write their software stack. At the end, it was so difficult to program it, so people gave up, and Nvidia actually take over this business. Right now, AMD are coming back, and wonder what the slogan that they are using, that they are software-oriented hardware. So right now, I'm trying to just to come from the different angle. They put all the software in open source. They even allows you to have some user-defined instructions, so you can actually tailor your system to do things more flexible and so on. They try to go back to the same field with a very, very different approach, somehow similar to Nvidia. So we'll discuss a little bit, but most of the lecture today will be based on Nvidia, because Nvidia is only 95% of the market in HPC, high performance computing, right now.
95?
I think that these are the numbers. Maybe I'm mistaken a few percentage here or there, but they dominate the market today. AMD are phasing out of the Xeon Phi. So actually, most of the accelerator right now based on, at least for learning, based on NVIDIA cards, we'll see that in inference, the TPU for Google and similar for Amazon, etc., are quite common. By the way, Amazon are doing the training in also Microsoft on regular processors, but we'll discuss it later. But the majority of the market, or if we look on the 500 HPC machines, we'll find out that about 90% of them are using GPUs or NVIDIA GPUs as an accelerator, or the way to get the performance out of the system. But, so, questions? Okay, let's start with the very, very, very basic. What is computer architecture? And again, since we have a mixture of people from that have an industrial background, including Intel, that most likely know very well this material. There are people that has no background with hardware. So I'll try to simplify many of the things, but at least to give the notion what we are talking about and why it is important. So let's start with the very, very, very basic, what is a processor, what is called a von Neumann model. So it is amazing that the model wasn't changed for the last 40, 50 years. A single core, what it does is fetch, decode, execute, memory, write back. This is the only thing that the processor knows what to do today, and most of the processors. What is fetch? You get stream of bits from the memory. How you know where to get these bits? You have a register which is called program counter. Program counter points to a place in the memory. And when it goes to fetch, it just look at the program counter, see its number 2054, so you go to address, physical address 2054, ignore for a minute its virtual address space, we don't like to complicate it, and take the stream of bits from that location. So, how the system knows to go to this address?
You have the PC, you just said, and PC is not enough.
Let's suppose that I started the machine from zero. Okay. I boot the system. Mm-hmm. I boot the system that check everything is okay, and what's next?
You have already memory chunk from where you booting the system, and then
how the system knows it?
It's hard-coded.
Yeah, there is some hard-coded address, but it can be hard-coded or it can be sometimes if you're afraid that you will have some errors in this, but you start with some address, you go to a location which is always this location. Usually you have there's something like a small program that we call a bootloader, and then this bootloader start to boot the BIOS, and then the BIOS operating system. The operating system initialize all the system, and now we are up and running. So we fast forward this is quite a complicated process, and you're up and running. Now you want to run your program. So you run your program. How you run your program? Linux, how you run your program?
You just execute it. I mean,
yeah, there is an instruction. Execute name of a program. Okay, so assume for the simplicity that the loader take all the program, put it into main memory. Now what? How the system knows that I should start? Where is my main?
yeah, there is some protocol, when you're executing a binary. So when the binary was compiled the first time, so it was under some agreements. So now the system knows where to find it.
Almost true. It's not true. Yeah. I cannot. Yeah, but the point is that usually the executables are in a file that has a clear format, and this clear format just has something that we call header. And here in the header there is a place which is the entry point for your system, for your device. Now, what's happened? This is also binary file. What is binary file? It has zeros and ones. So suppose that I will take some disk that it has songs and try to execute it. What will happen?
An error.
I can do it. I can take any kind of disk. I can try to execute it. What would happen?
It's unpredictable.
It is very predictable.
The loader won't find the magic number and
Okay, exactly. What is the magic number?
which format?
There is some agreement, and here there is a field which we call magic number, and the magic number, with many other things, tells you what is the binary. For example, I say songs, but maybe I compile it to ARM architecture and I try to run it on Intel architecture. So of course I cannot run a binary which was compiled to Intel on ARM architecture. So first of all, you look on this magic number, and this magic number tells you what operator actually it encodes the system, the operating system, etc. And then it shows that these binaries are fitted to the architecture that you are using. By the way, it is not true when you run binary translation or virtual machines, because in virtual machine we can go from one machine to another, but anyhow, it needs to know this is Intel code. And also, I have here, in the header, I have here some. So, first of all, if I try to write ARM architecture on Intel, what I will get? You'll get an error which is very interesting, wrong magic number. Which means, I don't know what to do with it. It's magic, I don't know. But also, if for example, I can compile a different models, and only then I link them, and only after I link them, I can execute it. What is the difference between something which is partially compiled and something which is executable? The difference is if here I have the pointer. If here in this field I have a number which is a pointer and it is not -1, it means that this is executable, and the first thing that the system does is to take this number and put it in the program counter. So now after you put it into the program counter, so when it reaches to the fetch, it goes to the pointer where you actually tell this is the beginning of my program. And after you execute the first instruction, what's happened?
The next instruction goes.
Automatically, if it is not jump, so automatically in RISC architecture, by the way, do you know the difference between RISC and CISC?
For what?
RISC is reduced instruction set, and to make it very simple, all the instructions are on the same size. So you know exactly that if you start with storage 1000, the next one is 1004, and the next one is 1008, etc., etc. In Intel architecture, it is variable size, so you know that if you start with 1000, the next one is somewhere. So you need to know what is the instruction, and only then you can fetch the next one. Not true. But we'll discuss it later on, because what's happened, since Intel wants to decode few instructions in parallel, so they actually take all the combinations, and because of the front end or the decoder, it's much more expensive in Intel than in any other architecture. But anyhow, fetch just take a string. Let's look on the RISC architecture. 4 bytes from a pointer counter, bring them, and now you do decode. What does it mean, decode? Decode says what is the instruction, what I need to do with it. Do I have to add, or if I have to subtract, etc. And also, many times it encodes the registers. Add register A with register B and put the result in register C or register A, etc. So it says what you want to do with this instruction. But in my architecture, I have integers and I have floating points. So how I know it's written add, how I know that I need to add floating point or add integer?
You have some indication? You have special registers for
No, it's just different opcode. Even though this is add and this is add, it has different opcode for add integer and add floating point, that's all. So by the way, the system doesn't know anything. So he may take the same place in the memory, and if you tell him that this is integer, he say, okay, so this is integer. If you tell him this is floating point, the same string of bits, he will say, okay, this is floating point. The system is very, very, very simple. Doesn't have any notion of anything. So now you execute, and if needed, you go to the memory. Why to go to the memory requires execute? What you need to execute if you go to the memory?
Maybe address.
You need to know the address. So execute in memory accesses is the operation that actually calculate where you load or store from, and then you go to the memory. Memory here can be again, it is register, so you don't need the memory, and then you write back to the place that you need to write. Very simple. Very simple, but what is the performance that we can get out of this simple model? If we assume that we are fetching one instruction at a time, so in the best case, and again I assume that I pipeline, which means that I don't need to complete the entire flow in order to fetch the next one. By the way, it's important to distinguish between latency and throughput. What is latency? Latency in this example is file. It's how long it takes you from the moment you fetch until you finish the operation. What does it mean, throughput? Throughput, I'm just looking on the end of the pipeline, I just look how many instructions on average I finish every cycle. And this distinguish is extremely important, and we'll discuss it later. So in this case, if we pipeline, the best that we can get is one IPC. And usually one IPC is not good enough, but even worse. Because usually in such architecture, we are not be able to get one IPC. And the reason is that if you have in the pipeline, actually the length of the pipeline depends on the slowest stage. Which means that if I access to the main memory, and access main memory today can take you few hundred cycles, so very easy you find out that everything is stuck and your IPC is dropping down. We'll discuss it later. But in the best I can get one IPC, and we want to get more than one IPC, so what we can do. And so, there are different techniques in order to improve the performance. So, in the past, the best way is to run in faster clock. We run in faster clock, so we still have one IPC, which means instruction per clock, but in a second I have more clocks, so I get more instructions.
What's IP?
Instruction it was supposed to be IPC. ILP is you're wrong. It is a typo. It was supposed to be instruction per cycle, IPC. ILP is instruction level parallelism, which means how many instructions in parallel you can execute. But it was supposed to be IPC instruction per cycle. By the way, I didn't put the slides yet on the web, so I hope that I remember before putting on the web. Correct. So, again, if I run in faster clock, the problem is that I consume a lot of power. And we'll discuss it later. So I can use pipeline, we said it before. I can try to execute instruction in parallel. How have I execute instruction in parallel? There is something which is called Flynn law. By the way, it is not true, it is not really accurate. They said that you cannot produce more than you consume. So if you fetch one cycle per instruction, most likely you will not produce more than one cycle per instruction. We'll see that in vector operation it's not true, but in general it's true. So what we can try to fetch and decode, for example, 2 or 4 instructions per cycle. So why we are not using it? Why we are not doing it?
We are.
We are. But what is the problem to do it?
Wide pipe.
What?
Wide pipe. You need to widen the pipe.
I need to widen the pipe. In Invert Architecture, it is very complicated because I need actually I don't know where the instruction ends. So what Intel does, they are doing, first of all, of course, speculation. They are doing general 2 things. One is the introduction of your code, your cache, that actually you put the instruction in decoded format. So if you happen to hit the same line that you already decoded, so you don't need to decode it again. So the save this stage, you save a lot of power. But usually the way that you decode in parallel, it can be very, very complicated, but the simplest version, assume that all of them are simple instructions, so they have minimum weight, and if you fail, then you go to a slower path and try to find the exact length that you need. In reality, it's something in between. But let's look on RISC. Suppose that in RISC I want to decode 16 instructions per cycle. What's the problem?
Dependency.
Dependency, but even it's a kind of dependency. There is something which is even more fundamental. And the more fundamental is the fact that I have jumps. If I have jump, so what I decode? We know that naturally about 80% of the jumps are backward. which means that if I go backward and I not continue, so if after 4 instructions my pointer goes backward or jump forward, but it's not continuing on the first pass, what we call jump taken, doesn't matter if it is forward or backward. If it is taken, so all the rest of the decoding are not needed. We don't know what to do with it. So usually, if your basic block
Can't you
is...
cache it for later?
What?
Can't you cache it for later? Because eventually you will not taken.
But
Yes and no, it's not simple, you cannot do it in one cycle. So in the past, we use a structure that's called a trace cache. In a trace cache, you actually keep the instruction in the order they were executed, regardless their order in the program, and speculatively. And if you find out that this time the order is different, then you execute them one by one.
Trace
So-
cache is not used anymore?
No, trace cache are not using anymore. By the way, I think that this is about time to bring them back, mainly because the only architecture that I know that used trace cache was P4, and P4 doesn't exist anymore because of many other reasons. But in P4, because of implementation issues mainly, the trace cache wasn't very efficient.
Your cache is different from trace cache?
Yeah.
Ah, so
Your cache is the granularity of single York. Trace cache is the aggregation of many York cache in the order. So if you, for example, if I have here instruction A, B, C, and here I have jump to A, so in the trace cache, I will have a trace which will be A, B, C, A, B, C, A, B, C. Suppose that my trace cache is 3 times. So I unfolded it because I keep the instruction in the order that they were instructed, and I don't need actually to keep the jump. The jump, I just need to check that the branch was taken, and as long as this condition is correct, so actually I have this trace. So now I can decode all of them in one cycle. More than that, if they are decoded, so I can use them. So this is the idea of trace cache. Okay, and then there are issues that you try to element install. We will discuss a little bit about all these techniques. Again, it depends on your question to what depth, and then we can improve the memory. Now, for each one of these items, there are issues, and we need to be careful when we actually implement it. Anyhow, all of these techniques requires quite a lot of power, and if you remember from the first class, today we are limited mainly by power and thermal. This is what limits us. We can, in theory, if we, and this is what people are doing. For example, there are demos that show that Invert Architecture, ARM or AMD and so on can run in 586 gig. How you do it? You put it in helium in minus 180 usually, and then you can run it as fast as you want, because the design allows you to run much faster, but the heat actually stops you. So this is the main limiter today for processing, not that we cannot execute it faster, but we cannot control the extra power that it produces.
the heat dissipation of the unit, of the chip himself, or was it total system heat dissipation?
So now it depends on what system. Usually what really help you is the thermal. And the thermal, Do you know the difference in general between energy and power? Power is how you consume at a point, which impact usually the thermal. Energy is how you consume in unit of time or when you execute some job. So if you are battery operated, you care about energy. If you're the one who pay the bill, you also care about energy. But if you say, I don't care about money, I want to run it fast, so you care about thermal. Because when it reaches some thermal point, you know what's happened? This is the best case. It just melts the silicon, and now you have sand again. So you start with sand, you end with sand. So this is physical. It's not a matter that. So usually you have sensors that prevent it, and then the system just stop. But and then you can blame Microsoft. But anyhow, yeah.
Would parallel processing help in this?
Who?
Parallel processing.
Yeah, there are many techniques to prevent it. What you're doing in reality is that you have a thermal control, a power thermal control that when the chips start to heat up, so you automatically lower the frequency. So this is why people says that thermal or power is equivalent to performance, because if you try to heat a system, so actually the frequency will drop down and then you lose performance. So, by the way, the only company that allowed to go beyond the limitation, but only for a short time, is Apple. I don't know today, but at least in the past, because they want to give you the feeling of a good response time. So they said that for a very, very short time, if you just move the mouse and you want to see that the mouse moves smoothly, so they allow the system to go even beyond the thermal for a very short time, just very fast, and then they drop the frequency back to keep the health. But this is very dangerous, and usually most of the companies don't do it. Okay, so
let's continue.
So let's talk a little bit about the memory hierarchy. By the way, all the reason that I'm going through all these details is not just to give you a lecture on computer architecture, but mainly because later on you will see that Nvidia or the GPUs, or what we call now throughput computer, will go method by method that we describe now, and will do the opposite. So in order to understand why they do the opposite, first of all, we need to understand why we are doing something, and only then we can actually talk why they are doing the opposite. So the purpose again will be to show you why they are, why in CPUs we are doing it in one way, and in Nvidia they are doing it, or in accelerators they are doing it all the way different. Okay, memory hierarchy. So memory hierarchy, again, the main purpose of memory hierarchy is to reduce the average access to the memory. So in theory, you could have a very, very fast and large memory. In the past, Cray, for example, had that time, very fast and a very large memory, again, for that time. The only small problem is that if Cray used to cost something like $10 million, about $5 million were because of the memory. So any one of you that want to buy this laptop and pay $10 million, I know how to build fast memory to this one. For those who don't like to pay $10 million, we need to think differently. So the idea is, again, since we are, the rule of 1090 usually holds. Usually, in machine learning, it doesn't, but usually it holds. So it is good enough to keep what you really need in a relatively small structures, and these structures are the fast. And this is what we call L1 level. at this L1 level, I'm not going into details, is very fast and actually it works only at the speed of the main memory, or the processor. So. Then you have L2. L2 and L3, by the way, they are built on the same die, so in theory, they can run on the same speed as the L1. L1 on purpose is built in a different way because L1, because it is relatively small, it's active most of the time. L3, if you just look on it, many of the ways there are relatively random, rarely used. So in L2 and L3, L2 is in intermediate, but in L3 we mainly care, not only, but we also care about leakage power and not only about active power. So without going to all the details, we built it in a different way, and the trade-offs are different. Again, you build something different if you want to access very fast, or if you want to save leakage and active power. These are two different ways to build things.
Yeah, or SOM technology?
All of them are SOM technology. But in one, just a small example. In L1, if you access a tag, so you fetch all the different tags, you fetch them to comparators and by all the different data in order to save cycles, so you could actually retrieve the data as fast as possible. In L2 you don't care, or L3 you don't care to pay one or more cycles and to reduce the power to send all the data and all the tagging power. So the way that you build it is different. There are many other differences, but I'll not go into all the details here. It's not that important right now. But just to explain to you how important it is, CPI is clock per instruction. By the way, why we use sometimes IPC and sometimes CPI? IPC is instruction per clocks, and CPI is clock per instructions. It's very simple. Usually people like to get numbers larger than one, so they prefer to say, okay, I execute 2 instructions per cycle, or it takes me 2 cycles to execute the same instruction. But these are the same. It is just a matter of presenting it. So if we say that we have only 1% miss ratio on the L3, and suppose the L3 is 1,000 cycles. By the way, in graphics, as the memory is 1,000 cycle access time. So if you have 1% miss ratio, you drop your IPC and everything else is ideal, you drop your IPC from 1 to 11. 1%. So you need to be very, very careful to either to get a very, very high hit ratio or to do something else. So the problem with machine learning that the XNN is for RNN, CNN, you name NN, etc., all the different techniques. So usually the other space is large, and so caches are not always effective, at least not in the simple way. So the way to handle large data that doesn't fit in your memory, what usually you are doing?
Save it on disk.
What?
Use the disk.
Again?
You use the disk.
No, it's too slow, you cannot.
So you need more memory.
Yeah. It reminds me that many years ago there was a company called Digital, and whenever you told them that the performance is not good enough, they tell you, okay, BMM. BMM stands for buy more memory. It doesn't matter what you do, buy more memory, it will improve your performance. So this was their slogan. Anyhow, we want to take advantage of the cache. I cannot increase the cache because I need to reproduce my core each time, and it is difficult to go to the manufacturing each time that I change the parameter of the matrix. And we said that we have only small cache size. So what we need to do is to change the algorithm. And we'll discuss it later on, but there are algorithms that we call them block algorithms. And by the way, it is true not just for GPUs, it's true for CPUs and any kind of system that have hierarchy of memories. Many times in order to optimize the algorithm to the architecture, it is not enough to deal with the architecture, you need to change your algorithm. So how you know, for example, so there are algorithms that actually change the algorithm in respect to the size, the physical size of the code that they are running on, but how they know, I said execute, how the system knows what is the size of the cache?
It doesn't.
Of course it knows. I have a system, I want to run it, and the system wants to adjust itself to the size of the cache. How the system knows what is the size of the cache? There is a special instruction which is called CPU ID, and the CPU ID actually keep you all the information you need on the system, include how many hierarchies of memory you have, what are the sizes of the memory, what memories are shared, what memories are not shared, etc. So the software today, when you write the software, you can go to this instruction, and there is a special format which is common to all the architectures today, and the CPU ID just tells you all these parameters. So when you run on the architecture, you can first the question can be what is the sizes of the cache, and then you can actually adjust the size of the blocks that you are using according to the architecture that you have in the system. So again, you can see that in many cases there is a synergy between the features that we are doing in the hardware and what the software needs, because otherwise you cannot optimize your system. Okay. So this is all I wanted to say right now on cache memories. We'll go back to this slide later on. So if you look on a regular, this is just an example of, I think that this was the first Ivory Bridge, or one of these codes. By the way, it was published before Intel actually announced that they have graphics codes. So originally it was a code with X, and it looks like a code that they disabled, but actually this is the place for the graphic codes. So you can see that just to show the majority of the die is for cache.
This is the ring architecture?
This is
A ring architecture?
This was a ring architecture in this case, but it doesn't matter. I think that only recently Intel moved from ring architecture to mesh architecture, and this is mainly when you start dealing with the 16 or and above cores before they use the ring architecture. So you see, this is the proportion. Here about 60% is L3 cache. But it is not really true, because it is much worse. Because the core itself includes L1 and L2 cache. And the branch prediction has another cache, which is the cache for the branch prediction. And all the other mechanisms. So if you just calculate, the very rough estimation is that about 80% of your core is dedicated for structure which are a memory. Memory of different types, but they are memories. So, and you have less than 20%, which is really active or actually do something. So the computations is only a small fraction of your code in such architecture, but in general, it is correct. And we'll see that in graphics, it is the opposite. In graphics, most of the area is for active core, and they are using much less area for memories, and again, we discuss why. So we said that if you fetch one instruction, so you can produce only one instruction. This is almost correct, but in one exception, which is called vector operations. What is vector operation? Vector operation just take this loop for int equal 1 to n, and you see that if you do ai equal bi plus ci, so there is no dependencies between the instruction. You say, okay, if there are no dependencies, I can actually issue the same instruction to array of ALUs, and each one of the ALU will execute the same instruction on different data. This is why it is called single instruction, multiple data. So this is the way actually to span, and you fetch one instruction, but you execute 8 instructions. This is the idea of vector architecture. And vector architecture actually is quite famous. In the past, I think that the first vector architecture NMX was designed here in Haifa, in Intel first, Dr. S, where then today AVX2, it is 16 wide packed floating point. It is on Skylake. I assume that MD is similar, I'm not sure. AVX, by the way, this is still not very widely used because the software is not there yet, but AVX is very, very common on Intel architecture. There is something similar in ARM, there is something similar in IBM, and all of them use the same idea that one instruction operate on different or in parallel on many data points. So this is the way to execute things in parallel. I'll take a few more minutes, and I just want to finish the CPU part, and then we'll take a break. So, another way to reduce stalls is use a lot of speculation. And in the code we are using a lot of speculation. It is branch prediction. Branch prediction need to predict the branch if it will be taken or not taken. By the way, how I use branch prediction?
You have some small history of
yeah, I look on the small history, and according to the history, there are a few algorithms that I can predict the behavior of the next one. And remember, this is one of the most profitable issues, and the reason that I'm saying it is that there was a guy that when I was in Intel, he worked very intensively in all these algorithms of the branch prediction, and then he just implement few of these algorithms on stock market, and actually right now he try to predict the values of stocks market by using branch prediction. So there are very practical ways to use speculation and such algorithm. But on the serious part, today we are doing branch prediction by using machine learning. For the last, it started as a theoretical work in the academia. They put Perseverance, and they found out that using very simple machine learning algorithms on die can give you very good results. Most of the companies are still using what we call a two-level branch prediction, which is the most common algorithm. Again, It was invented in the academia. We are doing a lot of prefetching. Prefetch is to try to access data we haven't fetched yet, but we assume that we will fetch, that we'll need it in the near future, so we bring it earlier. There were a lot of work about value prediction. Right now, value prediction doesn't exist in any processor, but in the last conference on Invert Architecture that was last week, we had a session about value prediction, and there are a few companies that are interested.
When you prefetch, you bring it to the cache? Where you bring it?
Okay, so usually, today, yes. There was some work that showed that they try to put it in a scratch pad or in temporary buffer before you bring it to the cache in order to eliminate, to throw things that you really need. Right now, most of the time that you prefetch to the L3, and L3 is large enough to assume that it doesn't pollute your cache. But,
what's the latencies for L3 access?
It depends. L3 accesses in Intel, this is used to be between 40 to 80 cycles.
40?
Yeah, 40 to
That's
80.
a large penalty.
Is yes and no, because in out of order you can compensate something like 16 cycles without losing performance. So but it is much better than to go to the main memory.
Yes.
There are other mechanisms that try to prefetch from L3 to L1. So all this issue.
You have this in power? You prefetch from L3 to L1?
Yeah, but all this issue of prefetching is a big issue. I'm not going to go in right now, but actually there are two mechanisms. One mechanism is allow the hardware to do it. So the hardware track your access patterns and bring things to the cache according to some assumptions. For example, if I'm accessing address X and then access X plus 4, I may assume the next time I will access X plus 8. So this is called a stride prediction, or next line prediction, or there are some algorithms which are much more complicated for prefetching. And there is a software prefetch that you allow your user to say that I want to prefetch this and this and this exact data, because I know that I'm going to use it. By the way, software prefetchers are very tricky, because usually they are excellent for one generation. You take the same code and you run it on the next generation, and you find out that usually you drop your performance. Because the software prefetchers are very accurate, which means that they are very sensitive to the real latencies. So whenever you change the ratio of the latencies, so many times it doesn't locate anymore in the right place. This is the reason that it is.
Yeah, but if I want to optimize for certain hardware,
Yeah.
it's a good thing to do.
Yeah. For certain, this is the reason that most of the time people are doing it either if you JIT your code, because the jitter can know you the specific architecture, and then it can actually put it in the right places. In the right places depends on the architecture itself. Or if you are in a situation that for any new generation you recompile your code, this is not very common. In embedded system it's very common, but in general purpose it is not common that you recompile your code, because if you recompile your code you need to test the code again, and testing takes you a long time and effort. So people prevent doing it. So you can, for parallelism, either within the execution, will not go into all the details, but out of order is something which is very common, which means that you fetch things in order, then you ignore dependencies, and actually you execute the instruction according to the data dependencies, and not according to the order. that appears in the program, and then you have something that we call commit, that you commit them in order. So from outside, it looks that you have something that go in order and go out in order, but inside, you allow instruction to bypass each another in order to reduce the probability that your system will be halted because you have long latencies. So there is a VLIW. VLIW is a technique the compiler actually tells you which one, what instruction can execute in parallel. So this is, again, it was found to be very efficient to DSPs and embedded system. It is not used anymore in general purpose. The last architecture to try to do it on general purpose was Technion. Not a great success.
Yes.
And
Was Tina?
what?
Tina was also VLI?
No. VLIW was the only VLIW machine that actually consumed a lot of power. It was amazing how VLIW was originally was supposed to be low power design, and the joke was that you could actually boil the water by these coals because it was so hot. But again, I don't like to spend more than that. The last thing that I want to mention, which is very important to our discussion, is multithreading. Multithreading is the user actually breaks the system into threads. And so the user tells the system these are the segments of code that can be run in parallel. So the system do not need to look what are the instructions that can run in parallel. If it belongs to different threads, it means that it can. The user tells me that it can run in parallel. And then I can use the same resources and do one of the things either to the left one is just to schedule. This is the in order superscalar. I have the width, and if I have stalls, I have stalls. The second one is what we call interleaved. So we say thread 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4 in order. It sounds very similar. Atom, the first atom of Intel works in that manner, and it has pluses and minuses. The other is switch on event. I execute something until I have low latency, and then I switch to another thread. Or I can partition my system, or in architectures like Sandy Bridge or most of Intel cores, they're using something which is called SMT, simultaneous multithreading, which means that I decode from different threads, then I allow it to execute in any order in between. I don't care, and then I commit them to different strings.
Don't you want to separate the L1 for a thread to prevent cache migration and stuff like that?
There are many different techniques. Usually you are not doing it because you want also to optimize in the case that you have only one thread. If you separate it, so you end up that you are not using the entire cache. So it is not simple. Usually you are not separate the cache. You can, if you, for example, in a real-time system that you want to guarantee some performance, so many times you are doing partitioning because you don't care to how the other threads because you care about the guaranteed time. Otherwise, usually you are not separating caches. But there are different implementations, more aggressive, less aggressive. Just in very, very high level. One word on power efficiency, and we'll take a break. As we said before, systems are very, very sensitive to power, and this is the reason that we need actually to take power efficient approach to everything that we are doing if we want to get low power. It is quite easy to get performance and lose a lot of power. Usually the rule today is that you need to get a performance advantage 3x versus the power, if or 1 to 1, if you want to put a new feature in your system. But most of the companies, whenever you propose, or papers or whatsoever, if you propose a new feature, the first question is, okay, how much power it will consume. And this is the reason that usually people are talking about energy efficiency, which means that it is power multiplied by the energy. This is the criteria today to judge new algorithm in architecture. They try to balance between the performance and the energy that it consumes. Questions? Okay, if no questions, so we'll pause here, we'll take 10 minutes break, and the next, I'll switch to GPUs, and we'll start to see that none of the assumptions that we described in the CPU will keep. We'll just see how they change all the mechanisms one by one. And in the third part, we'll start to discuss special architecture for machine learning, like what Nvidia are putting today in their GPUs, which are tuned to machine learning. Okay, so this is I'll skip this one. These are slides that just show why we move to multiprocessor in general, and not on die, but multiprocessors in general, and ignore all the equation. The conclusion is that as long as enough parallelism exists, is always more power efficient to double the number of cores rather than to double the frequency. You assume that in either case you can get twice the performance, either if you double the frequency or you double the cores. In reality, it is always more efficient if you have enough parallelism in the system to work with simple cores, and many of them, than to work with large and more powerful cores. And the other thing is the thermal, because of thermal limited, we just said before that power equals performance, it translates for each other, but I will not go into details. So, we look right now on the three different architectures right now. So this is Intel Core graphic processor with 4 cores. This is Nvidia, and this is AMD. Again, this is the graphic cores of AMD. Unfortunately, this is not colored, but the color code here is that here you can see that the green is the active code. So this is the logic, it's actually do operation. And if we say that in this architecture about 80% is memories, so in this architecture about 60 or 70% is logic. How come? Why they can put 60 or 70% logic and Intel cannot put it? So one simple answer is that this run in about 3 gigahertz and this run in less than 1 gigahertz. Sorry. This one is 3 gigahertz and this run in about 1 gigahertz. So it runs slower, but you have many execution units. But it is and AMD, it's the similar. AMD has a different internal structure. Maybe next class we'll talk about the differences between AMD and Nvidia. But in general, we see that it is different. And go back to the decision that we make when we execute code. So the first question is, do we really need speculation? And the answer is no. So why we are putting speculation? Let's put it speculation because we optimize for latency. So if you don't optimize for latency, what you can do in order to handle the system without speculation, it goes back to the 19th that Agrawal in MIT produced is an architecture that's called Alwaf. Alwaf says, instead of doing prefetching and going and try to find what we are looking for, etc., which is very, very powerful and requires compiler, etc., let's execute until I have L to miss. As soon as I have L to miss, I switch to another thread. Which means that on die all the time, I keep a context of n processes. So the switching time is very similar. I just move the pointer from context A to context B. I don't even to load. I don't need to load the context because the context is indirect some pointer. This pointer tells me which context is the active at that point. So this was the idea. Execute something until you hit some stop. You hit the stop, move to the next context. Execute the next context until you hit some stop, move to the next one. Hopefully, when you move back to the original one, the problem was resolved. Which means you need to have some logic that if you have an L2 miss, will continue in the background to resolve the L2 miss. But in parallel, you can continue to execute another context. So, from the hardware point of view, there is only one thread which is active at the time. So all my pipeline is tuned to a single thread. But because I have multiple contexts, so I just need to jump between them. Great idea. So while Alwaf was failed, miserably failed, the reason was that Agrawal actually built a system, and he built a system with 64 cores, and he hoped to build a system with 256 cores, and you need to have 4 contexts per core. So the software people said, to have 1,000 threads in parallel? What kind of software you think that you can run on it? And this was the end of the project. Because at that time there was no workload that actually needs that many threads. Fast forward, when the graphics people start to ask themselves, what are the alternatives? Oh, we do have millions of threads. Because in graphics, each pixel is a thread. So in graphics, we have plenty of threads. So we can do it in Alwaf way. We can go back to the basic, and we don't need. Alwaf is much more efficient because it needs resources only for one thread at a time. So, again, speculation, you can, by the way, you can resolve branch prediction that way, you can resolve misses that way, you can resolve many things in that way. So, from that point of view, again, what is the cons? The cons is that you increase dramatically the latency. Because now you have a miss, so you do something else, but it is not that when you get the result back immediately to continue to execute it, you need to wait until your turn will come back. So the utilization is much better, the latency is much worse. So you cannot use these techniques to anything which is latency sensitive. And latency sensitive is something that we call general purpose. In most of the general purpose programs, we are latency sensitive. You can use it if you are throughput oriented. In a throughput, what you care is the throughput. You don't care about latency whatsoever. Well, when Intel tried to build the first graphic cores, that it was called Larabi, and again, Larabi was a total failure. And the reason was because the team that built Laravel was originally came from P4. They had, the tradition was to do things as fast as possible. So they produced something that can produce graphics with a very low latency, with very high power, which is totally the wrong premise. But again, the Nvidia, on the other hand, understood that you need to change the trade-off because you have a lot of parallelism in the system. So we'll go to it in a minute, but before that, I want to because we will discuss accelerators, there is something which is very fundamental in accelerators that we need to point out. What is the difference between accelerator and multiprocessors?
Again, what is the difference between?
Accelerator and multiprocessor.
How the CPU give it task?
What?
It's how the CPU, the host, give you task, and then it gets the results.
Yeah, the point is, again, we try many times to break this symmetry, but the idea in general in accelerator is the master is the core. The core actually controls the accelerator. The core, and we'll see it in CUDA, the core actually tells the graphics, I want you to do this job for me. And so I send you the data, I send you the instruction. When everything is in your side, I will tell you, now execute it. When you execute it, you report back to me, and I'll decide what to send you back. So this was the very, very basic. Later on, they break this symmetry, but the basic idea in accelerator is that the CPU is master, the accelerator, which is the slave or the acceleration provider. So, in the past, we have a floating point. Floating point it was accelerator. Floating point used to be a different chip. You send it from your program, you send it to the floating point operation, and you got the result back. So this was purely accelerator. What's happened is that after it became a standard, and after we had enough cells on the die, we could spare the space, so we integrated it inside. And by the way, for many years it was integrated in such a way that they kept this notion of a master-slave, and it took them a few years actually to build a new interface to it. But, for example, if you look on the first Microsoft box machine, the gaming, so they use two power architecture with one SIMD engine. This SIMD engine could get work for the two cores and execute it and return the results. So they have one accelerator that actually serves two cores. So this was the basic architecture for the game. GPUs, on the other hand, usually they have separate memories. So the host has its own RAM, and the device has its own RAM. By the way, the modern architecture, they have something which is called a virtual unified architecture. And actually, we view these two RAMs as one, but still, technology, this one is built usually out of GDDR, which is different from this one, which is built out of DRAM. There are two different architectures. So regardless if you can view them as one or not, the idea is that you have two different entities. This is the master. If you want the GPU to do something, you need to transfer the data from here to there. And only when it is there here, you execute it from the main memory to the execution unit, you get the result, you copy it back. So even though in the modern architecture, which is unified, you can actually ignore it because you can access it from the CPU to the GPU, from the GPU to the CPU. Even now, it is more efficient actually to copy it because whenever the GPU need to go to the host, even though it can do it, it is extremely slow and it slows down the process. So if you want to have a good performance, usually it is a burden on the system, but you need to copy it from one set to the other. We'll see it in example. Yeah.
Are those SP notations?
We'll discuss it later on. This SP is like a small codes which are dedicated for graphic operations. Or for, you can view it as an operation of one item on the vector machine.
They multiply and add?
Yeah, but in a few minutes we'll expand it because it's very specific to the Nvidia architecture. And by the way, they keep changing the names all the time. So Nvidia has tend to use the well-known common names and just use them in the opposite direction. So what they call thread is not what Intel called thread or what the rest of the world called thread, but they still call it thread. And then they have a core and they move the F2 SP and then they move it to CUDA core and now they call it tensor core. So the names are floating, which is good for marketing, but you always need to translate. Oh, this is this. So it just mean a new generation, of course. So the name is differently, but the basic. We'll deal here with at least in the beginning on the first architecture, which is 10 years old, very old, but the very basic notation or the very basic mode of operation is still valid today, but the name changed, many of the details changed, but the basic mode of operation changed, kept. And the main reason is that this, even now, these cards are still being used for graphics. And many times the graphics determine what you can do and what you cannot do. Nvidia usually don't have cards which is purely for computation. Usually this is still called GPU, Graphic Processing Unit. And they meant it support graphics. Even though many times it's overkill because in most of the gaming boxes, you don't like to put a card that costs you $5,000. But it's still supported. Yeah.
Can I have another question?
Yeah.
I'm confused because we said that, or maybe we didn't, that's what I understood, that we want or we prefer to sacrifice latency so we have more throughput, and throughput is very relevant for X and N's, and any
and for graphics.
But graphic means response time. It is latency.
Yes,
I want the next frame to appear exactly.
Yes and no. Graphics sense you need to deal with millions of points. So what you really care about the response time. But if you are not utilize your resources correctly, it will take you forever to execute it. So you're right that in graphics you care about the latency, but the latency where the portion between the amount of parallelism and the amount of execution unit that you have is so large that what you really care is about the utilization of the execution units. Mm-hmm. And the number of work divided by the number of active or actually active cores gives you the latency. So if you want to, it is not, let's say it doesn't give you the latency, but it has a large component of the latency that you will get. So you don't like to take it into extreme, and the latency will be very, very bad, but somehow you need to balance between them.
So until some fixed point, it's not a trade-off.
Yeah.
It's not necessarily trade-off.
Yeah.
I can improve latency by improving throughput until some point, and from there, it's a trade-off.
Yeah, so
Okay.
but again, from our point of view, we don't care about the graphics. So
Yes.
from our point of view, we say, okay, in reality, what they're doing in graphics, they define few functions which take the long latency, and then they put them in special purpose hardware. So they just extract this operation, and you'll see they have something that they call SFU, which is special a hardware accelerator inside the graphics for some operation like sinus, cosinus, some complex functions. And this is mainly, it used to be mainly for operation that causes the long latency in the computation. So this is their way to balance. Now we'll see that my assumption, although it is not written anywhere, that they will start putting the ReLO and all these functions which are for machine learning, because now these functions become to be the bottleneck of the machine learning. So we'll start seeing functions which are also functions which are dedicated for machine learning as part of this small accelerator. But we'll go to it in 3 minutes. Okay, so this is the start actually that it is quite complicated, and this is quite old because this is Vista. I think that this is the only thing that remains for Vista. And the Vista was an interesting operating system. When they introduced Windows 7, I remember the manager of the Windows 7 had some press conference, and he said, "You don't believe we are so efficient that we are even if more efficient than XP." Vista was after XP, but people knew that XP was more efficient than Vista, so he just ignored this product line. And later on, somebody asked me about Vista, so he said that in customer service there are 2 levels of customer satisfactory, which are good, bad, Vista. And this was his quote, so I do not. Anyhow, this is from the Vista, but I think that the general structure of the graphic stack is still quite the same. And the idea here that at the level of the user, you write things which are on the frame of the graphics. In computation, actually, we have the notion of grid, something that is a closed form, and then you translate it to the kernel. The kernel needs actually to take care how it is represented on the GPU, and to translate, because the GPU until very recently didn't have virtual memory, it only had physical memory. So you need actually to translate the virtual to physical addresses. And after fixing all these references, so actually you send the code knowing where are the buffers and so on to the GPU and ask the GPU to execute. So you can see that you have this module, which is the VID memory, which is the memory management of the graphics. And you have here the GPU scheduling that you tell the GPU, now you need to execute something. When you tell the system that you need or you can execute something, you just make sure that you already finished to copy all the data from the CPU to the GPU, meaning that all the data is in the GPU side, you can schedule it. So this is the way that it was done. It's still mainly done in this way. There is an attempt, again, this is, you cannot see a lot here, but AMD come with something that called HSA. HSA, the main idea is to allow to access from the user level directly to the GPU without going all the way to the operating system. It is quite complicated. I will not go into all the details, but they are also using RDMA, which was invented in InfiniBand, but it is widely used. So they use all this structure in order to have communication between GPU to GPU, GPU to CPU, directly to bypass many things. Nvidia start to have something similar, but still, when you work with Nvidia, usually today, you still have this GPU scheduler, and the CPU tells the GPU what to do, with one exception, that in the last, I think, 4 years, I think that it started with CUDA 6, they allow a piece of work, what they call kernel, in CUDA, to schedule another kernel. And the idea was, for example, a good example is, suppose that you want to process a face. And we know that around the eyes there are many, many more details, so you need to do it in much finer granularity. So if you just distribute it evenly, so you end up that the process that works around the eyes will have much more work to do. And since at the end of the day, everything needs to be synchronized, so this determines the amount of work, the amount of time that it will take you to process a picture. So what they are doing, as soon as you decide that this is an I/O that you have a lot of work to do, you can break your work to n subsystems, and then to reschedule these n subsystems. So now you spread something that requires more dense computation to more CPUs to execute. So actually you can balance between different parts which are not even in the first place. So this is something that it is something like a recursion execution, and they add it to CUDA 6. But rather than that, usually the CPU schedule work to the GPU and has full control. So how it does it? Again, I will not go into all the details, but you put the CPUs and the CPU 1, 2, GPU, you can have more than GPUs, and each other at the user level can actually schedule something on the queue, on the work queue of the other. So each one has a work queue at the level of the user, and you can actually launch a work and ask the CPU do something for me, or the GPU do something for me, or one GPU can schedule something to another GPU. So each one of them has a visibility to the work queue of the others, and you can distribute the system in much more flexible work, and you can actually handle in this way a heterogeneous system much easier.
This is only ARM architecture? AMD architecture? Also
No,
for NVIDIA?
actually this was invented originally by AMD, but at the end of the day, it was a consortium of many companies, excluding Intel and Nvidia, and the success was very minor until lately, because the consortium caused a lot of latency in every decision, because different companies usually have some politics between them. It is even worse than politics between different departments in the same company, which is hard to believe. So it took them forever. I think that at some point AMD took it back and actually take the lead. And right now, at least in their AI chips, they have support for HSA. At some point, we thought that it will die, and now it's back in AMD's AI chips, and it makes a lot of sense to do that.
So HSA, it's a company, or it's a
No,
concept?
HSA is a heterogeneous system architecture.
Oh, so it's a concept.
Yeah, it's a three-letter acronym like any other three-letter.
Because it has this beautiful logo on the
Yeah,
upper right corner.
yeah, because this is a consortium. and you cannot establish a consortium without a logo. So first you have a logo, and then you have a consortium. Who likes the logo? Okay, so these are the GPUs, and as I said before, I hope that it will take 5 minutes. We'll pause here, and then I'll continue until 5:30 is the last part on the GPUs. Let's continue GPUs. So GPUs, as we all know, was started as a graphic accelerator. And very soon people start to realize that it has a lot of floating point power and a lot of other features which are good for many other computation frames. So even before CUDA was invented, people start using all these graphic languages and try to cheat the system. And so the system will think that these are computations on pixels, and actually it was computation on arrays. And then Nvidia said, okay, we need to make a business out of it. And again, the brilliant idea here was to put the software team and the hardware team together and to produce something which is software hardware for design. And we'll see how it impacts all of their decisions. So in general, GPU is throughput-oriented design. So as we said before, it's not that latency is not important, but the solve latency in other means, and the GPU its main purpose is to give you the best throughput. And again, this reason of latency was the reason that in the past they had the fixed functionality for GPUs, but then they saw that every modification, any change in the market, even if you want to react to something to the market, or if you have a new game that you want to optimize for it, so if you use a fixed architecture that everything is done in hardware, it is not flexible and takes you forever the runtime. So they decided actually to move from the graphics to more general purpose, and then they start putting a general purpose core for graphics and some fixed hardware to deal with special functionalities that they have for the graphics. We'll address at least two important parts of the special functionality that they have. So they decided that it will be energy efficient. As we said, it is very important. So what does it mean, simple control? Simple control, no branches, no data forwarding, simple prediction, if at all. So in general, officially they don't have any prefetching, for example. In practice, we proved that they do have some prefetching. We just made some experiment and we show it, but it's very, very limited in very, very specific cases that we want to solve some specific problem. But it is very simple algorithm. They don't try to do anything sophisticated. They say, okay, the software can do it. We trust the software that the software guys can be very smart. So we trust the software guy. By the way, this is the first time the hardware people said they can trust the software people. But this was the decision. And what's happened if your software doesn't fit to this model? Don't use the GPU. They don't try, even at least in the past today, and a little bit try to help the non-conventional software. To have and say, okay, if you have software that has massive parallel, or let's say that the ratio between the sequential synchronization and the parallel is that relatively has much more parallelism than sequential code, we can support. So why it's so important? Because as we said before, if you have parallelism, you don't like to use most of the existing mechanisms. There are other solutions, and it is not that they invent these solutions, but they use existing solutions, but in a smart way. Let's look on the solution that they put in the GPUs. So this is a very old graph, but the ratios are still the same. So this is Ivory Bridge versus AMD Radeon, and we can see that the transistor count is much higher in the AMD, in the graphics. The power is around 3 times in AMD, but if you compare the flops, is 17 times higher. So if you just measure power per floating point, so since this is increased 3 times, this is 17 times, so actually you get a very good proportion that these cores are very effective for floating point operations. Yes, this is
What is simple predicting the previous slides?
the previous.
Yeah, simple predicting something.
No, I said simple predicting, if at all, officially they don't have any prediction. I said that when we actually did some experiments, we found out that in some cases they have something that we think that this is prefetchers. But officially it doesn't exist. If you just examine it, you can see that there are some patterns that the only way to explain it is they have something like a very simple prefetcher, but again, officially there is no a prediction at all. And the next question will be, okay, if you don't have prediction, how you do branches, how you do data prefetching and so on. And we already have some of the answers, and we'll go into more details soon. So we already spoke about throughput processing. The main idea is that all first of all, the system will be balanced, which means that both the communication between the memory and the CPU will be 100% utilized, but also all the execution will be 100% utilized. So this is the goal. Usually you cannot use it. Either you are memory bound, and then the processing unit, some of them are idle, or you are a CPU bound, and then the communication is not 100% utilized, but you try at least to balance between the processing and the data movement. By the way, the simplest way to do it is to have something like a double buffer that you execute on half part of one buffer. While you execute on the buffer, you have some DMA that bring you information from far places in order to fill up caches, or they're using scratchpad to fill it up with data. If it is balanced, when you stop, when you finish executing the one buffer, so you can switch, and now you can work on the first one. If you have 3 buffers, so you have better chance to balance the entire system. It is design point that you can design. Okay, but what are the implications? The implication is that as a software, if you want to run something in an efficient way, you need to understand the design space, which means you need to understand for a specific design, a specific card, what is more efficient, what is less efficient. You need to understand a lot of internal information about the hardware that you will run on, because otherwise you cannot 100% optimize it. Many times people say, okay, 80% is good enough, 80% it is relatively easy. To squeeze the last 20-30%, usually this is the more complicated. You need to optimize a compute kernel, and usually you need to do it bottom up. What does it mean bottom up? You need to start with some experiment on your device and to see how it reacts. What is the sensitivity to different sizes and so on. We'll discuss in a few minutes what are the parameters that you deal with, and only after you understand it, then you can go to the big picture and do the design, or use existing libraries, and you hope that the existing libraries already did much of the optimizations that you like. But even if you use existing libraries, very soon you find out that there are at least 10 different libraries, and the question which one to use is very dependent on the nature of your program, the nature of the application that you use. So you need to understand the system, and you need to establish intuition. This is something that's very simple to say. It is a little bit more difficult to implement. The reason is that suppose that you have n possible optimization, and there are known optimizations. Many times the order that you implement this optimization may result in totally different results, because this optimization may depend on each other. So, but after implementing few examples, you start getting the intuition what is good or not. One of my students right now tried to have a machine learning that will tell you in what order to do the optimizations. So, by the way, it started to be more and more common to use machine learning to optimize machine learning. And the next level will be to a machine learning that will optimize machine learning that optimizes machine learning. So we have a lot of ways to progress. Okay, so I'll do it very fast, and if it is too fast, stop me. What is a GPU? GPU in general, this is what they call a shader core. Shader is just the notion of simple core for graphics. We will not go, but this is general purpose graphic, general purpose core, simple, very simple core. And you have something which is called text. Text is something which is very unique only to graphics. When you deal with graphics, so usually you make the computation without taking care on what is the color and what is the shape and so on, and only then you put the colors and you put all the other parameters on the top of it. And so you can take something like a ball, and it can be football or it can be the earth, depends on how you paint it later on. And this is the text that tells you, okay, which one of the point that the result, what color, what shape it has. So there is a separation, but this is something which is very specific to graphics. But in some places you can even use this one in a very, very efficient way, because this is not a regular cache in the sense that it doesn't order in rows and columns, but it has some internal structure which is more like squares. So you put the internal structure actually allows you many times, if you work in tiles, to access tiles in parallel without having a conflict on resources. So I will not go into details because we are not going to go very deep into the graphics, but into the GPU at that point. But just remember that sometimes if you have some tough problems, you also use the text more than that. It has a different channel, so if you have problems of bandwidth that come from the memory or from caches, so if you can get it from the text or from the memory, you're getting more bandwidth of the system. So people sometimes are using it. And then you have a few blocks, hardware blocks for special purpose task that in this case it depends on the graphics. And then you have here something which is called work distributor, and the work distributor need actually to take all the work that the system needs to do and to distribute it among all the shader codes. Will show how it is done in CUDA in a minute. So this is the CPU style that we have a fetch, a liu, execution control, which are the registers that we need to swap each time we have data cache. we have out of order, control logic, etc., etc., etc. We said we already covered all this, and the idea number one is slim down the code. We don't need all this because we don't care about the performance of single thread performance. This is the first understanding. If you have enough parallelism, you couldn't care less about the performance of a single thread. So again, if your application is latency sensitive, this is not true. But if your application is not latency sensitive, or if your application, even if it is latency sensitive, but it doesn't have, it is a kind of balance, so each one of the threads are doing almost the same work, so you don't really care to do out of order or to try to optimize the single thread. So you say, okay, I will have small, simple code that even run in relatively slow frequency, but I will have thousands of them. So the idea number one is remove all what is not needed, what we put inside in order to execute the single code. It is speculation out of order, fast access control, etc. And then again, single thread is not needed. But we still need to use we want to utilize the parallelism, and then they go back to the SIMD idea. But what is the problem with the SIMD? The problem with the SIMD that SIMD today is a fixed length. So you have a different opcode for SIMD MMX, or SIMD AVX, or SIMD AVX2, etc. And the compiler need to know, and the compiler need to do the optimization, and you need to know how to break it down. They said it is too complicated. So they said, from the software point of view, we will use variable size vector. You don't care what is the size of the vector. But the hardware, at the end of the day, the hardware is specific. So they invented the notion of wrap. I always confuse between WARP and WRAP, so maybe I made a mistake as well. Anyhow, the idea is that right now is the common that it is 32, but sometimes you use half wrap of 16. But as a user, you don't care. As a user, you write a vector. Actually, you even don't know when you write it. You even have no idea what will be the size of the vector. How it happened? Because you write your algorithm from the point of view of a single instance of the vector. So if I have a vector which is, I'll show you in a minute, but if I have a vector which has n elements, so I say, okay, I will write something to place I. I will give you a method to know what is I, and then my algorithm will be AI plus BI equal CI. For this one, I couldn't care less what is the length of the vector, because I'm writing it from the point of view of a single instance of the vector. How to do it we'll show later. But this is quite revolutionary, because you don't write the program by knowing all this information, but you write it in a very flexible way. I'll give you a method to calculate what is I, and then your code looks like that, and it is independent if I am talking about a vector or matrix or cube or whatever. Just the same. So this was the idea. Again, software hardware interfaces. They told how you implement it, they told how you write it in the case of the solution. So, this is of course if you have the way to have a parallel execution, so you get much more. It is quite obvious. Okay, I'll skip it. We'll come in a few minutes with examples of you using it. So the second question is what we do with branches. So they use techniques that actually many systems, include ARM, use it much before them, which is called predication. What is predication? Predication is a bit that says, suppose that I have a vector and SIMD instruction. I have an SIMD instruction, but also I have a bit that says, when I implement add, what are the elements that which are active in that cycle? So for example, I can decide to take, this is vector A, this is vector B, and this is vector C. I can decide that if I even C of I equal A of I plus B of I, else C of I equals 0. How I do it? I cannot execute at the same time. See, in vector, all it is single instruction, multiple data. So I cannot actually, at the same cycle, do the if and the else. So what I'm doing, I have a predication. The predicate actually mark with 1 all the elements which are even. And then I say, okay, now everybody do C of I equal A of I plus B of I. Since all of these elements are marked as 1, the predication is on, so now all the even are added. Now I go back, I flip the predication, all the zeros and 1, all the 1 and 0. Say, okay, now do everybody please do C of I equals 0. You see that I'm getting the same end result as I'm executing if. The only difference is that I don't need to, I don't have loops. I execute it like a sequential code that I parse it twice. So on one hand, it is less efficient. On the other hand, I don't need to take care about branches. And in their case, it was very efficient. So this is the if x greater than 0. So all the elements which belong to this one will execute this y equal power, etc., etc. So it can be more than one instruction. It can be a set of instructions. It can be an entire block. And then for every if, I need to repeat.
But internally, this if else will behave like this. Will use this mechanism for every if else.
Yeah. The next question: what I'll do if I have a nested if?
But hardware checks for this bit, right?
What?
The hardware, I guess, scheduler or something checks for the bits.
Yeah.
So
They have it for every operation all the time.
Mm-hmm.
And this bit, by the way, can be, in this case, it was set by the if. But I can, as a user, I can give you a pattern. I say, you don't care why. This is the pattern that I want to set the predicator. Mm-hmm. Predicator is a register, and the register, the predicator, if the wrap is 32 bits, so the predicator is 32 bits. I can set it I can, in the if actually set the predicator, but if I want, I will set the predicator because this is what I want to do, and it will be executed accordingly. So what's happening if I have a nested loop?
Just not moving this.
I have 2 bits. So they have few bits for predication. And then actually, you can have nested loops, but then it costs you a lot because 2 bits, if you have nested, so you have 4 options and you need to pass it 4 times.
It's exponential.
Yeah. So this is the reason that it is not recommended to have nested loops.
So
Because nested loop immediately will be
nested if or nested
translated.
loop?
What?
Nested if or nested loop?
Nested the same. Each one that you have an if, it doesn't matter if they because of loop is an if for the purposes. No, sorry, nested if. You're right. Nested loop it doesn't cost you. Because in loop all of all of wraps are the loop. Nested if. I understand. So again, this technique was used by other architectures, but it allows them to eliminate totally the need for branch prediction because they don't have branches in the sense that was used before. Okay. So having stores, we discussed it before, and again, they are keeping They are keeping a few contexts, not 4. They're using a different context in parallel, and they just jump from one context to the other. So, okay, this is not a big deal. We saw it before. Not really. So I'll just give this example. So we'll go very fast. We already did it. So let's jump over it. Now come the trick. How many contexts you have? Is user defined. The system doesn't tell you how many contexts you have per unit. By the way, the basic unit in the GPU for scheduler is called SM, which is streaming a speed streaming processor. This what you saw before. And the rule is that as soon as I assign something to SM, I cannot move it anymore. It belongs to this SM. So how many contexts I can assign to SM? It is user-defined. What does it mean user-defined? Each core has a pool of storage. It is pool of very fast storage, and this storage is used both for registers and for local data. Now, the maximum number of contexts that you can use is how much you devote for a context, divided, multiplied by the number of contexts that you have. Since this pool is fixed because this is hardware, so you can choose the trade-off. You can have more registers and less contexts, or you have the vice versa. So this is user-defined. And this is totally different from what we are thinking or used to do in regular architecture. So you can decide that you want to divide it into small contexts. So you see, on the above, you know that you have 8 ALUs. So each one of the contexts need to have at least place to keep the values or the context of the ALU. And you also have an area for a scratch. So each one of the ALUs, how many registers it has, you define, compiler define. So now the minimum is the number, the number of registers plus few for control that the system uses, multiplied by 8 because this is the context of all the ALUs. And then the other is the amount of shared or local data which is attached to each one of them, and you consider it as a scratch. So now you can, what are the trade-offs? If I have many threads, it means that I can actually go around many contexts before I go back to the first one. So I can actually cover long latencies, which is good. On the other hand, I have few registers, which means that I have a lot of spilling code, which means that I'm creating more misses. So it is up to me to decide, or up to the architecture, to decide what is the optimal point, and there is no recommended point. Again, you need to understand the impact of your compiler on the performance. You need to understand what is more important, and then you have the number. So this is the 1 minute before this is the medium, and of course this is the big one. So you have only 4 contexts to deal with, but you have a lot of local registers. You know that in some application, many registers allows you actually to run for a long time before you need to go to the main memory. To other memory.
What is spinning code?
What?
You said spinning code.
The spinning code is that you don't have enough registers, so you copy the context of the register to the memory, and you bring something else to the register. This is a common terminology in compilers. Yeah.
The scratch memory you mentioned.
Register.
What is?
Scratch memory.
Oh, scratch pads is instead of having. Sorry. Usually there are 2 ways to handle memory. One is a cache, and in the cache you have no idea what is in, what is out, because there is algorithm, and the algorithm is doing something like hashing, and it brings, and if you have conflict, it replace things, etc. The other option is that you allocate data, and this allocation, it is a user control cache. So the user actually, you don't let the hardware to decide what is in, what is out, but you actually manipulate this cache. You decide how many, for example, in this case, usually it will be local variables. How many local variables you have? So if you have a lot of local variables, so the compiler knows what is the amount of data that it has. So it will put them in some of them in register, some of them in this area. If it doesn't have enough in this area, so you put them in what is called local memory, but the local memory we'll see in a minute is in the main memory. So it starts writing to the main memory, read to the main memory, and this will cause you a lot of latency when you execute. So this is just the scratch when the meaning is a user-controlled memory which belongs to the process, which is controlled by the compiler in this case. Yeah.
But this is like share memory among all these.
In a minute, I have a slide that says exactly what is each one of the memory. In general, the answer is no. The answer is that this is like a local memory, but in a minute. Okay, so let's go. This is a very high level, and the reason that I use it because many of the terminology actually remain the same. So actually, the system itself is divided into codes, or what they call TP, transaction code. The transaction code is divided into SN, which are streaming processor, which are you see here you have a 2 streaming processor. The streaming processor actually share what they call parallel data. The texture are shared, and between transaction codes there is no coherency. There is no mechanism to copy things from one to another. This is the reason that as soon as you assign something to work to one of these SMs, you don't move it. You cannot move it anymore. So now if we dive in a little bit, so these are the TPC. Each one of them has 2 SMs, as we said before. Each one of the SMs This already changed a little bit. These are the execution unit. That actually this is the vector that they are using. The reason is that this was correct mainly for graphics, and they just adopted from the graphics. And here is the SFU. SFU, this is the shell. In this case, is the floating point, which later on become the 64-bit floating point. Inside here, you have only 32-bit floating point. But here you put all the specific hardware that you need for domain specific. So later on, they start putting there things like sinus, cosinus, etc. So you have one unit which is shared by 4 like this. So you have 2 units here and small units inside. Again, the internal structure changed a lot. The number changed, but the general structure remained the same. This is the reason that they brought it. So the structure is that they have the streaming processing. This is the processor. It is divided into small processor, which is the texture processor, later on they change it to transaction processor. And what is more important is the SM, which is the basic unit for executing something. Yeah.
If the thread is changing all the time, so how come the cache is usable? There was a cache in the picture.
The cache is going back going back to here. The cache is part of this one. So the cache is not real cache as we know in other systems. This is partition of the big area.
More like a
They
sketch.
also have L2 cache, which is different from this one. And the L2 cache came much later than this model. The L2 cache actually came to solve things like some synchronization that you need to have between the processors. In the past, you could synchronize things only by going to the processor, and it was much too slow. So the L2, in order for specific operation, they do require some data movement between the processing, but mainly for synchronization and things like that. Okay, so now we go back to the software. Because as I said before, everything is designed software hardware interface. So how you can use this structure? So first of all, the system supports only very simple data structures. The system support vectors, 2D and 3D matrices. Or in other words, it supports only matrices with 1 dimension, 2 dimension, or 3 dimensions. Now, the matrix itself is divided into blocks. There is no communication whatsoever between blocks. And the block is the basic unit which is assigned to SM. Once you assign a block to SM, you cannot move it. How many blocks you can have on SM? Go back to this slide. These are the contexts. These are the contexts of SM. So it depends how much data you need for the SM, and then you can decide how many SMs you can assign, how many blocks, how much data you need for a block, and this includes the data that you need for keeping the data and the data that you need for register, etc. And then you so you distribute the resources among them. All of these parameters are user defined, and this is the reason that it's quite complicated to optimize the system, because you need to decide how what is the structure, And there are many ways that you can actually take the block, even if you have a matrix. I can divide the matrix into blocks, I can divide it into rows, I can divide it into squares, I can many different shapes. It is up to me to decide what is the optimal assignment to the system. So each block actually is assigned to execute. What I mean here that I have some synchronization instructions. Some of them are implicit, some of them are explicit, which means that the way that I write my system is the host send what we call kernel, and we'll see in a minute example, to the GPU. Hey, execute this kernel for me. The GPU execute, and when it finish everything, it will go back to the processor, and this is explicit parallelism, because I finish, I send it back. But suppose that all the SMs, all the block, I just want to do read operation from main memory. The block actually will be divided later on to wraps, because wrap is the basic parallelism. And I have no idea in what order the wraps will be executed. I don't have any idea in what order the blocks will be executed or where they will be executed, but I don't have any knowledge in what order the wraps will be execution. This is where we said that we have two levels of parallelism between blocks and inside the blocks. So after I'm doing something like read, I need to have a synchronization about all the wraps that represent the same instruction, which is read. So I know that all the read operation in all the block have been finished. So they have a very sophisticated way to synchronize things, and synchronization, for example, between different wraps in the same block are done in extremely efficient way. So the WARP, I understand before. So this is the idea about grids, and each kernel may have different grids. So it's not the same grid that need to be for kernel 1 and kernel 2. But if it happens that it is the same in kernel 1 and kernel 2, so you don't need to send the kernel 1 again. If you know, the system knows that the kernel 1, that the grid 1 is already there. So if you use it twice, so you don't need to bring it back. So manage the system. So next week, I will go into all the details, how to write CUDA, etc., but in a very, very high level. CUDA is a flat model. What does it mean, flat model? Flat model, it means that I'm writing in something like a C. I'm writing both the CPU side and the GPU side. So I have one file, and in this file, part of it belongs to the GPU, part of it belongs to the CPU. Well, this is the reason we call it flat. And I mark what are the parts that belong to the CPU and what are the parts that belong to the GPU, and the compiler knows to distinguish between these parts, and then it knows to generate instruction to the CPU or to the GPU. By the way, something which is not in the slides. On the GPU side, you don't use assembly code. You use something which is intermediate language, IR, intermediate representation of Nvidia. Actually, you can optimize it. Also, they have a optimization guide. And the system translates it on the fly. So when it translates things from the CPU to the GPU, it translates on the fly. And why they are translating on the fly? Because anyhow, if you remember, the structure of the device driver that I show you, anyhow, they need to correct addresses. They need to do some operation because only at runtime they know the addresses. So they need to do some manipulation, so they do it at runtime, but more than that, they want to have the flexibility to have different translation to different cards.
GPU today still doesn't have MMU?
The latest, they have a very simple version of MMU, but it is still very, very basic. Again, I try to avoid as much as possible over the media. So the translation allows them to translate the same code to different architecture. And this is the reason that they can move from one generation to another and actually use the same code. And this is a great flexibility for them. It is like in Java or any virtual machine that you have bytecodes, you translate the bytecode for every specific card. This is what they are doing, partially in hardware, partially in software. So, short example. It's always a help to go down to earth, for sure. So, what I try to do here is just add two vectors. So on this, the CPU side, it's always int main. I have int I. See, on the GPU side, I mark it as global void, and when the system sees global void, vector add, it knows that this is a function called a vector add that will be executed on the GPU. So this is the way that actually I mark that this is something that doesn't belong to me, it belongs there. We see that there are a few other ways to do the system, but this is the very basic way to say this is belong to the other side. So why global? Because we'll see that I can also divide things like local and so on, and I tell the system put it on the local memory of the other device. So I can, but again, this notation, which is minus minus, this is long line, it's always minus minus, global. So let's look what I'm doing. It's a VI, AI plus BI. Again, I have no idea what is the size. I have no idea what is this vector. I have no idea whatsoever. By the way, this is not the real code. I'll show you the real code later on. And here, I call it, and this is a very strange notation, vector add, but then I have three opening, how you call it, and here I define what is the structure of the data that I'm transferring. This tells the system that it is one dimension, one with n blocks. And this is A, B, and C. So only at invocation, I tell the system what is the structure that I want, not before. So this is the general idea. Let's dive into more details. Just I will skip in a minute because I want to go to the same. Okay. Since we are toward the end, we have something like 5 minutes. I want to go over the real code and continue with the real code. If we have more time, I'll go back. So, let's look a little bit further into the code. So, I think that there should be. Okay. So, CUDA memory. First of all, I define in malloc structure on the CPU side. I define in CUDA malloc that I want to allocate data on the GPU side. Now, if I want to send something from the CPU to the GPU, So I define a array on the CPU side. Then I have CUDA malloc on the same size on the GPU side. And I need actually to use the instructor CUDA memory copy. And this CUDA memory copy can have copy host to device, host to host, host to device, device to host, or device to device. So this is a general copy that I tell the system from where to copy it. So now, instruction like CUDA mem copy usually will finish only after I go to the next instruction only after this instruction finish. But in order to be more effective, I also have an instruction that said copy asynchronous, which means start to copy now, and I will pause when I use it. So as long as I'm not telling the other side to use it, or I'm not asking to execute it, I can execute on the CPU side, I can execute many other things. Or even on the GPU if I'm not accessing the data. But if I access something that on the GPU side, that I am in a transfer right now, so it will pause me and make sure that the copy will finish, and only then will send the execution. So this is an example how you actually control the data, how you send when you invoke something. So you invoke it, so first of all, the system will check if this function already exists in the other side. If yes, it just says, okay, execute. If it doesn't exist, so it will send the instructions to the other side, and only then it will invoke it. Again, if I send something to be executed on the GPU, the system will check that the data A, B, and C are already either malloc, and if needed, they are the copy finished before I will execute it. Because otherwise I will get wrong results. So, I think it will have to okay. So now to complete the picture, and we'll finish with this one. Few words on thread scheduling, and I'll continue next class. Again, when I write something, I define the grid. Again, the grid is the data that will be used in a kernel that I'm executing right now. So I define the grid, blocks, etc. I'm sending it either, so I'm sending the data without the blocks, etc. I'm sending it to the other side. And then the block itself is all the instructions that deal with this portion of data. For some reason, the system randomly, or they have a mechanism to load balance between all the different SMs. You try to distribute it evenly. I just need one, I don't know why I misplaced one slide. Oh, no. Okay, I think that the problem is that it is hidden. One. Okay. The way I can't find right now the slide. The way that you define, that you know in what element you're executing, is that automatically when you define a block, the system generates for you a few parameters which are provided by the system. And the first parameter that the system will provide you is the thread ID, and thread ID on if it is on X and on Y. And the thread ID is this is thread 0, 0, 0, 1, 0, etc., etc. So actually, by looking on your ID on X and Y, you know exactly at what element in the matrix you are accessing. So the block, when it generates threads that belong to these blocks, actually generate the number of elements in the block. So each one has a different X and Y or X, Y, Z number, which are generated by the system, that indicate you are a thread that was originally generated in order to handle this point in the data. And this is the way, because the structure of the thread that I am generating is exact same as the structure of the data structure. So now Ci, actually this I will write that I equal the thread ID. It is X. This is not exactly accurate because this number is relative to the beginning of the block, and if I have many blocks, so actually I need to do some manipulation, because from the system point of view, this is continuous vector. So you have an indication what item in the vector your block start, and then you add to it your ID number, and this is the number relative to the start point of the thread. Same X, same Y, this is how you find. So again, to summarize it, and we'll continue, first of all, with the programming, it will be a little bit more clearer, and then I'll start to speak also about specific things for machine learning that they added. But the main idea here, a very careful design of software hardware, and to see what the hardware need to provide to the software, so the software can be written in a very simple way and will be transparent to the physical implementation.
Thread will work on a single pixel?
Yeah. A thread usually, okay, you can do whatever you like. It doesn't need, for example, if you want the thread to work on 10 items, so you generate thread, so you're referring only to thread 0, 9, etc. So you don't need to use them. But when you invoke it, so you can have a thread, you have ID to every piece. There is a thread which are divided by 10 will do something. The thread which are divided by 3 do something else. But there is identity between the thread and the location in the data structure. This is the reason that you can treat a single thread as a representative of a point in the data structure. Okay, this is a good point to stop. If you have questions, you're welcome. If you don't have questions, you're welcome as well, or I can take it offline. Yeah.
But the thread ID is same for both the CPU and the GPU bits.
No, it's only on the GPU.
It's only on the
Yeah, it is something only, this is a very good point. CPU, you treat it like any CPU. It is just C. On the GPU, because everything is relative, and because you don't know on what SM you will execute, so you lose the notion of order, you lose the notion of the structure, or of the vector, or the matrix, and so on, because it is partitioned and spread all around. So you need to replace it with something, so the system generates for you some marks that you can refer to this mark in order to know what are the part of the work that you need to do, your block, what is the part of the block that it needs to do. Okay.
Thank you.
Thank you.